Before the first flight of the space shuttle, models were tested using wind tunnels and computers. The virtual wind tunnel project combines advantages of both by placing a scientist directly inside a computer-generated flow field. CRTs present computer-generated wide-field stereo images from the user's point of view. A streamline tracks the user's hand position inside the virtual wind tunnel. It represents the path that a particle follows through the flow. A gesture controls a collection of streamlines that track the position and orientation of the user's hand. Note the divergence of neighboring streamlines. We can walk around inside a vortex, examining its structure in detail. Three-dimensional unsteady flows can also be visualized in real time. Here we see non-periodic vortex shedding past a tapered cylinder. This flow is visualized using virtual smoke emitters placed along each side of the cylinder. We can freeze time and examine these structures by walking around them. The virtual wind tunnel will provide the designers of aerospace vehicles an intuitive way of exploring complex aerodynamic flows.
Gear down and lock. Touchdown.
The design of modern aerospace vehicles, their geometry, their aerodynamic control surfaces, and their propulsion systems is dependent on precise engineering and vigorous testing. Before the first test flight of the space shuttle could be made, scale models were built and tested in wind tunnels to help predict how the shuttle would perform. Computer simulation, or computational aerodynamics, is being used in the design cycle to augment wind tunnel and flight testing. Computational aerodynamics can also be used to simulate test conditions that are difficult or impossible to achieve conventionally. The virtual wind tunnel project combines advantages of wind tunnels with those of computational aerodynamics by placing a scientist directly inside a computer-generated flow field. It gives the illusion of being totally surrounded by aerodynamic flow. Ames researcher Creon Levitt explains the goals of the project.
What we're attempting to do is use virtual environment technology to solve a real engineering problem. In our case, it's the interactive visualization of three-dimensional flows. So the whole point is we want it to be like a real wind tunnel, except that you are there and you're not disturbing anything.
To provide the illusion of being surrounded by flow, a unique head-tracking display system is used. A pair of video CRT monitors are used to present high-resolution, wide-field images in binocular stereo to the virtual wind tunnel user. The weight of the monitors is borne by a gimbaled, counterweighted, 6-degree of freedom motion platform known as the boom. Optical encoders at each of the 6 joints of the boom provide high-speed, high-precision information about the position and orientation of the user's head. A high-end graphics workstation renders the virtual wind tunnel imagery in real time, in stereo, from the user's point of view. Manipulation of the flow visualization tools within the virtual wind tunnel is accomplished by using an instrumented glove. The glove senses the position, orientation, and gesture of the user's hand. A variety of gestures are recognized by the system and are used to control the flow visualization process. A small, cross-shaped cursor tracks the user's hand position inside the virtual wind tunnel. A streamline is computed through the flow starting at the hand position. This represents the path that a particle would travel if it were emitted into the flow. A hand gesture freezes a streamline at the current hand position. Another gesture controls a collection of streamlines known as a rake. In addition to tracking the position of the hand, the rake also tracks the hand's orientation. Note the diverging behavior of neighboring streamlines. Some go above the wing and are caught up in the wingtip vortex. Others are caught up in the wing root vortex. And others go completely under the wing. We can scale the data and then walk around inside the vortex, examining its structure in detail. By simply changing databases, the user of the virtual wind tunnel can view other flow simulations. Here we're looking at a simulation of flow around an ogive cylinder at an extreme angle of attack. This is being used to test an experimental method for aircraft control. High-velocity airstreams are injected into the flow. Notice the complex asymmetrical flow patterns. Some of the most challenging computational aerodynamic problems involve three-dimensional flows that change over time. Here we see non-periodic vortex shedding past a slightly tapered cylinder. The flow is visualized by placing a line of virtual smoke emitters along each side of the cylinder. The vortex shedding process can be clearly seen. Smoke circulates for a while near the cylinder and then breaks off and travels downstream. We can freeze time and examine these complex flow structures by walking around them. A wide variety of interactive techniques are being developed to visualize these unsteady flows. The integration of these techniques is the next phase of virtual wind tunnel development. Team member Steve Bryson describes the project's future.
So over the next couple of years, what we're going to see is a very rich environment where the user will get into the virtual environment and have a wide range of options of ways of visualizing the flow that hopefully can change from one option to another very quickly. And the real challenge is to make all of those options very intuitive so that the user doesn't need to do a great deal of learning in order to use the system. He can get in and use it very quickly using all his intuitions. And that way he can concentrate on the science of the problem.
The Virtual Wind Tunnel project will provide scientists with a highly intuitive environment for exploring complex aerodynamic flows.